Good morning. My name is Anton Tronikov. I'm here emceeing the talk by my good friend Keerthana, and we are going to talk about robotics in the age of large models. We've got some slides to cover. I think we'll also jump in and sort of expository questions. This is a relatively high-level technical talk about the state of robotics today. It's very exciting. Keerthana is probably one of the leading researchers in this field, pushing the frontier forward. You also have a book out, which I'll let you shill when it's time. But for now, why don't we just jump into it? Why don't you first introduce yourself and then jump in the slides?
Hi everyone, I'm Keerthana. I live in SF, so I know a lot of people here, and I do research at DeepMind on robotics. I really care about robotics, so you'll see me geek out about it.
All right, well, kick it off. Let's go. You got slides.
All right, so this talk is about robotics in the age of large models. So I was thinking about this audience and what to present, and uh, just kind of thinking about where we have been and what are the works that happened in the last few years. So right when I joined Google was around the same time, a year later, we came up with SACAN. So this was one of the early works that used large language models for high level planning of robots. So here, a large language model, let's say you would give a request to a robot and a large language model would break up the plan. This was pre-chat GPT, so we had to use Q learning and a Q function as an affordance model. And affordance is determining whether a robot can kind of do a certain task. And that is how an LLM would break up the plan, which is then executed by a low level controller. Then in December of 2022, we came up with this work called Robotics Transformer 1. This is a low level model. What it does, or what it showed, was that you can kind of treat robot data like transformer data, like the vision language data that people train on, by tokenizing the action. So, literally, the joint commands that the robot gets can be tokenized, and now you can build a transformer on top of it. And then in 2023, early 2023, we came up with this word called PAMI, which is embodied palm. And the idea here is that you can kind of make this high level planner that was introduced in SACAN multimodal, which means that now the robots can see while they plan. Um, and later that year, there were a few other works. One was Robotics Transformer 2. So here we proved that you can kind of use a large vision language model in order to train these robot action data. And doing so means that you can transfer concepts from the internet, and robots can generalize. For example, a robot can identify who's Taylor Swift and who's Tom Cruise without that that information never appearing in any robot data set. Later that year was introduced RTX, and here we found that you can kind of train a model on all different robots, and robots are only as different from each other as English and Chinese, and you can kind of take advantage of the prior knowledge of across different robots. In 2024 was from late 2023 on to 2024 was the rise of diffusion models. So here we found that you can get very dexterous control. So here a robot is tying a shoelace, which was kind of impossible before. Somebody, a, a professor did mention that I would quit my job at the time when robots can tie shoelaces, and now we can do it very easily. Diffusion models are also much better at multimodal control, and usually this was done for single task dexterity.
Could you elaborate on what's meant by single task dexterity in this context?
Yeah, so here a different diffusion model was trained for a different set of weights was trained for different tasks.
Okay, that's an important distinction. Thank you.
So where we are right now is that frontier models have a remarkable amount of general intelligence. We know that Gemini can do IMO level math. We know that Genie can generate all these world models as well as have some sort of primitive control over it. And we know separately that robot models have been getting very good over the last few years. They can now fold shirts, do like assembly, and tasks like that. So now the question is, how do we combine the two? How do we combine the generalized intelligence of frontier models with the dexterity that we can leverage on top of robots and get generalized dexterity? This may be one of the last fundamental problems to solve in robotics. So one approach to this is, so you have the VLMs and the AI that kind of live in a world that is separate from the physical world. And then we have robot models, or the VLAs, vision language action models, which live in the physical world, can control robots. And now the one way to solve for generalized dexterity is bring them both closer together to endow the frontier models with more and more embodied intelligence, and also make the robot models closer and more general. So taking a general thing and then making it fit to the robot world, and taking a narrow thing and then making it more general. So that brings us to 2025 and Gemini Robotics. So this is an effort that started early last year, and it was about embodying Gemini and how we can endow Gemini with robotics world knowledge. And there has been several works this year on that line. So in February, we came up with Gemini Robotics, which showed that you can get very general, dexterous, and interactive control at a low latency on multiple robots, and it can be post-trained for different embodiments, including a humanoid, bimanual arm, etc.
What does interactive mean in this context as well?
Interactive means that a robot kind of reacts to a dynamic situation. So let's say um, it's trying to pick something up, but then the thing is moving, or it needs to place something there, but then a person is messing with the scene. But the robot has to react and
So this isn't generally available under the context of single task dexterity, right? You would treat interactive situations as a separate class.
yeah, no, yeah. So it is not necessary that a single task model needs to be also interactive. For example, if a model is like, if you have to speed it up 10x, then it's probably less interactive.
Got it. Okay.
Then in July, we released the Gemini Robotics on-device model. So here, the evidence or the conclusion is that you can still get a lot of generalization by optimizing the model with a very small model that runs locally, and it has certain advantages such that, like, you don't have to send data across the network. And most of my talk will focus on Gemini Robotics 1.5, which only got released like 2 weeks ago. The key message here is that we can now make robots agentic, which allows them to solve very long horizon tasks by searching on the internet, using tools, etc. You can make now vision language action models thinking VLAs, so they can think before taking an action. Uh, we also noticed that it is better to learn across embodiments, and we also noticed that embodied reasoning, you can get a SOTA embodied reasoning that beats even GPT-5 at a much smaller size. Some results here. This is meant for a technical audience, so let me know if you're bored, and then I can skip some of the slides. Uh, so we noticed that these models have become a lot more general, even across other baselines. And the what it means by generalization and why it is important is that, so in data-driven robot learning, you would expect that we can never collect enough data uh, across a lot of deployment environments. And we want to deploy robots in the entire world. So an important quality here then to optimize for is generalization, which means how does the robot react to situations that it hasn't seen before, based on the situations that it has seen before and the data that it has. And so there you test it by asking it new instructions in different language with typos, um, or different variations of the environments, different objects than it has seen in its training data, new visual variations, and the combinations of those.
Could I ask about some of those categories of generalization you've got on the slides? You've got instruction, action, visual, and task generalization. What is the distinction between, for example, instruction and task generalization?
Yeah, as seen in the slide, so task generalization basically combines all of the other types of generalization.
Got it. But could you give an example of instruction generalization?
Yeah, so let's say you have something in the data set that's like pick up X and then put it Y. So asking it in a different language
Got
would
it.
be an example, or asking it in a way which is kind of reasoning. Let's say you say, pick up the puzzle, and then you have multiple, or pick up the extinct object, but then you have, let's say, a dinosaur, a dog, and something else. So you have to do a little bit of reasoning to do the task.
So it's the same. It's different ways of asking the robot to do the same thing. Is that about right?
Something like that.
Okay.
Yeah. So it's changing the instruction
Got it.
and using reasoning in the instruction.
Got it. Cool.
Um, and I'm also gonna plug in some humanoid results because I recently work on humanoids, and I think it's one of the most important problems to solve in robotics. So we noticed that the 1.5 model is our best, most general model for humanoid, and by a large margin. Uh, Back in February, when we were working on Gemini Robotics, we had to kind of like post train a single task model for each different humanoid task. But now we see that with a single checkpoint that is shared across even other robots, you can get a lot of generalization. So here are some examples. A lot of people in the community think that solving last mile multimodality uh, cannot be done in a data driven way, and you need a lot of feedback, you need model based learning. But we noticed that the GR 1.5 model is really good. It can do a lot of multimodal uh, hand behavior implicitly and also explicitly. So you put a thin object in front of it and it goes like this or like this, and you put a big object in front of it and it automatically goes like this. And you can prompt it to do like two-fingered ambidextrous picks. You can ask it for, you put a long object and then it goes like this. So these are like different types of multimodal motion behaviors. We also noticed that it's very good at, it's much better than other models at dealing with unseen objects. And you can kind of get to a point where you solve like around 70% of the time. It can do very generalized pick and place from new objects, new receptacles that it hasn't seen before, just by asking for it. Here's a fun video that I made 2 weeks ago. So this is like, I'm just trying to play with the humanoid, and it's kind of like a toddler. And this is the worst that humanoids would ever be. Like giving a banana to a monkey, and it's trying to kind of reach for it, and it's doing active perception and manipulation. And I'm not giving it to it, and I'm trying to mess with it. And it works with kind of seen and unseen objects rather similarly.
What is
So
the distinction here between active and passive perception?
So active perception is like it has to notice that I have taken the object from its hand and moved it away, and it's a single model, right? So it's like the vision in, actions out, and it kind of reacts to it.
Gotcha.
And it's not just tabletop. You can also do kind of similar things in a lot of different environments. One feedback that we see for a lot of humanoid data is that it's very like pick and place like, and that is true because people are limited by the dexterity of the hands. But even with pick and place, you can pick and place by itself is not a single task. There's a lot of variations around it, like heights and um, situations. Next up, I want to talk a little bit about thinking VLA. So far, you have one model that is acting, and it has no notion of interpretability. It doesn't process text or output text. Um, However, we noticed that by training these models on thinking data, you have a way to introduce the test time compute scaling for vision language action models. And here, the way that the model thinks is it has a hierarchical thinking where it is thinking about next steps and it is thinking about low level motion. So, literally, like where to put your hand, when to close it, and so on. And by training a model this way, we find that it has emergent interpretability. It has some notion of planning and implicit success detection. So here it's like trying to pack some objects into the bag, and you notice that as soon as one task finishes, the instruction changes to pick up the next thing because it has a notion that the previous task succeeded. And then, for example, so here it is trying to pick this object with the right hand, and then it missed it, and then it goes with the left hand because the plan changes. Now, all of this would look very rudimentary for people who are very familiar with the AI world because AI is like much smart. It can solve math and all that. So like, why do we care about these little things where it's trying to pick something up and the plan changes? It's because the manipulation models are still very primitive and they kind of live in different worlds. And we are, at least the goal is to bring up the physical intelligence to the level that we have for the digital, the mathematic, the scientific intelligence. Otherwise, we would be in a world where like the AI is doing all the science and the creativity and the paintings, and we are doing laundry and dishes and everything that needs moving things from one place to another.
Hans Moravec strikes again.
Mhm. Yeah. Okay. Here's an example. I'm gonna fast.
Could I ask a few questions about the thinking model? So when was this sort of thinking model released? This is a very recent result, right? Two 2 weeks ago. Um, that's incredible. I haven't seen this result yet. So because I wasn't at Coral, and if I was there, I would have seen it. Um, I did not know about this result before this talk. I'm actually like frankly astounded that this works. What maybe I should ask at the end of the talk, but I would really like to understand the relative scale of the pre-trained model, which has this sort of RL post-training for thinking applied. Like roughly how big is this relevant relative to an equivalent language model in parameter size? In
I did not understand your question.
GPT is X billion parameters. How big is the pre-trained model that you're doing the RL rollouts on here for the thinking post-training?
So this is thinking on a VLA, not on
Wow.
the VLM.
Okay, so this is actually even
So this is
completely different
different.
domain.
Exactly. So this is not. Yeah, this is not like the LLM thinking.
So this
Yet.
is thinking in joint torques.
Yeah. So it's
That's
thinking on a
incredible.
model that is embodied.
That's
Yeah.
incredible.
It's thinking on top of an action model.
Maybe that was a little bit too inside baseball, but could you break down the function of a VLA a little bit because again, this is actually really truly astounding to me. So I want to really reinforce the import of this result. Could you explain a little bit like the structure of a VLA just at a high level, right?
So let's say you have a GPT-5 or a Gemini, and then you say, well, here's my robot, now make me coffee. Those models cannot do anything because it is not embodied. It cannot control a robot. It doesn't know where to go to do what. But if you ask it, solve this math problem, it will do it. So a VLA is um, a specific type of model that is usually post-trained from a VLM in order to control robots. So the outputs that it does is the joint torques or like
Direct actuation, basically, right? It turns it into the signal that actually moves the robot's arm,
Yeah.
right? So, okay, so the procedure for creating this thinking VLA is to take a large-scale pre-trained VLM, which is just a multimodal LLM, right, more or less. I say just like it's easy, but we do post-training to achieve VLA. So in other words, we somehow add joint torques as an output head to our large pre-trained model. Now, so I understand how we do thinking rollouts on an LLM. How do we do thinking rollouts on a VLA?
kind of very similarly, but by adding the thinking data. So now,
What does the thinking data look like? Because the output is joint torques.
so yeah. So the conclusion here is that if you want your robotics modeling problem to be much closer to the AGI, physical AGI problem, then just learning action torques is not, just modeling actions is not enough. So you kind of have to model what you're thinking as well as what you're doing, because what you're thinking is very fundamental to influencing what you're doing.
Right.
Yeah.
Right. I'm just curious because in thinking rollouts for LLMs, we generally have some sort of verifiable reward that says, okay, this reasoning chain got you to the action that you wanted to perform. But it's very difficult to express success or failure in the form of joint positions and action tokens, right? That's where I'm trying to cross the boundary. How do you cross that boundary?
It is not very oral based yet.
Okay, I see. Okay, that's important. But this is like again, this is truly an astounding result, and also the fact that the reasoning chain is interpretable is just incredible.
Correct. Yeah.
Wow.
And it kind of allows the robot to act for more than like 10 to 15 minutes because it is changing its thoughts, and you can see very nuanced behavior sometimes just because of the thinking and the steerability of the VLA. For example, if let's say you want to it would like push the boxes away when it is needed to do that. Um, it would automatically start doing retries, which was not possible with just an action model before.
Ladies and gentlemen, the astonishment that you're seeing on my face is 100% genuine. I've never seen this result before. I've just hugely updated on where the frontier of robotics is today. This is incredible. It's like truly, truly incredible result. Holy hell.
It is kind of a new paradigm, and also you can run these VLAs with thinking on and off, leading to very different behaviors. So here I'm just messing with the environment of the humanoid. Maybe one point that we're trying to show from here is that earlier, a lot of robotics demos, if you've seen many on Twitter and stuff, they are in very fixed locations. If you move the objects a little bit, then it would no longer work. But they're really great demos. It gives a perception, uh, but it's not a sign that things are actually working. This is a demo where like a person is actually messing with the scene and the robot kind of reacts, and it shows that you can't kind of hard code these demos.
Yes. Yeah, no, this is fantastic. I'll let you continue with the presentation.
And we noticed that for medium long horizon tasks, this works really well. Another important result from this is that so previously, what a lot of people do in order to train a robot brain for multiple different robots is they just naively co-train on all the data. Second thing that people do is like they train on one robot where they have a lot of data and then they post-train it to fit all these other bodies. But now we find that you can kind of have one checkpoint that controls multiple different robots, and it becomes state of the art. And also, by doing so, you can transfer motions that has not been seen on a certain robot from another robot.
Is actually someone teleoperates the robot, so they have to physically move the robot. And right now, what he's doing is he's training the robot how to do a task. So traditionally, people will train a single model per robot. In Gemini Robotics 1.5, we're actually using a single model across multiple robots. So here's an example where hanging things from that workbench. One of the key things in 1.5 is that now all of our other robots can actually do the same task. This actually works on a completely different robot, which is the Aloha robot.
What a time to be alive.
Very nice.
What a time to be alive.
I was very surprised that this transfers to a humanoid. A humanoid is like very different.
Never seen this. This is a great example of a completely new motion that is able to learn with the Aloha robots and not just transfer here.
Yeah, this is absolutely fantastical.
And so the idea here is that even if let's say you are trying to solve for humanoids, maybe what you should do is not just train on humanoid data, but train on all robots data with motion transfer explicit alignment. And more examples of how different tasks transfer to different robot. This was collected on the humanoid, but now and by man, these two other robots can do it. Next slide. And transfers from Aloha to the humanoid.
So maybe it's interesting for our audience to know about Aloha, because this was a pretty interesting advance as well, even though it's a little bit more on the kind of like economics and engineering side. Yeah, it might be interesting just to checkpoint that.
Yeah, so an Aloha is literally just two arms, two Troughton arms. This is work from Chelsea Finn's lab in Stanford and led by Tony. Um, and the main innovation there is that you can build a very cheap robot that's scalable, but it has a lot of capabilities in terms of dexterity. And Aloha can tie a shoelace. In order to learn shoelace tying, you need to first collect shoelace tying data. You need to be able to teleoperate a robot to do that. And Aloha expanded the frontier of what people thought you could, what kind of data that people thought you could collect with robots.
It made it much cheaper to collect data at scale. What year was Aloha? 24 or 25?
Late 2023.
Late 23. So I have no idea when anything is happening anymore, because things are moving just incredibly fast, even in this space.
Yeah, and now everyone's on mobile Aloha, and now like even the Aloha is like so outdated. It's all the Chinese exons and stuff. Okay. And lastly, I just want to touch on embodied reasoning. So something that I mentioned in the first half of my talk, which was like making the VLMs more endowed with spatial knowledge. So the embodied reasoning kind of pushes on that effort. So you can do like pointing, but you can also do complex pointing. So here the question is, in what way does the water flow? And it says from here and then here and then here. And there are interesting ways to combine this with robotic capabilities. For example, you can say where to go to pick up the cup by and point to that particular thing. You can ask for success detection. You can ask for progress understanding, and this helps kind of orchestrate the robots. And Agentic kind of brings it together where you can take a high level model and then a low level model and then put them together to do much longer horizon tasks.
So this is essentially the equivalent of tool use in LLMs,
Yeah.
something similar to it, right? What sort of affordances or tools do you equip the sort of robotic agent with, the physical agent with?
We'll search the internet now.
It'll search the internet.
Use my location and sort the objects into the correct compost, recycling, and trash bits.
From the story cast based on C perceptual waste guidelines, I will use the green bin for compost, the blue bin for recycling, and the black bin for trash.
So this is not a task that the robot has collected a lot of data on, but it is basically combining the search data, the pick and place, to do something that's very semantically meaningful.
Right. Is this behavior, the tool use behavior, built into the base VLM, or is it something that gets trained in at the VLA?
This is on the VLM.
On the
Agentic
VLM,
is on the
okay.
VLM.
Lots of highly technical questions, but I won't bring those to this talk. Like, how do you make sure you don't overwrite the tool use in the VLA post training? But that's like a really inside baseball question. Very cool.
And here's an example of how you can combine the different capabilities. So the VLM can do pointing, trajectory prediction. So you can literally say, well, sort all of these objects in their right location, and then so this goes here, and then the VLA can just follow those instructions given by the VLM. And doing so and combining these tasks in or doing the agentic framework is much better than just orchestrating with Gemini 2.5 Flash or just using VLA alone. And lastly, safety. So there's also a benchmark now which asks for the Asimov benchmark around safety. So here, like,
They named it the Asimov benchmark. That's sick.
yeah, talk to peer.
Look, it's nice to know that there's still some nerds working in robotics.
Yeah, this is a very large team. I'm just presenting all their work. And also, I had a book. I wrote a book that came out in May. So if you want to learn more, this is a good resource.
This is highly recommended. This textbook, by the way. This Keerthana's kind of shy about this, but this is probably the only textbook that's actually up to date on what's actually happening in frontier robotics today. Highly recommended here. I have no financial interest in this, by the way. I just think it's a really good book. Sure.
That's it. That's it for my boring slides.
They were excellent slides. Are you kidding me? You literally got astonishment out of me. Me, the jaded roboticist. Of like, so one thing the audience ought to know is Keerthana and I are roughly of the same generation of roboticists. So I started in robotics in a serious way in 2015. You said 2017.
I said 19.
In 2000. Well, that was Google, but you started earlier than that in robotics. So much of what we just saw, even up to 2020, absolute science fiction. Like that robot tying a shoelace is not only did it seem impossible, but we did not seem to even have an angle on it, even up until a few years ago. And now you can do it in a very low cost way on this Aloha platform. I really want to impress on this audience just the pace of acceleration. A lot of it does seem to be driven by the discovery of large scale pre-training, right?
Imitation learning.
Imitation learning.
Yeah.
So talk about that a little bit.
Yeah. So I think this was probably 2022. So with RT1 line of work. Prior to that, and I joined Google like a year before, and everyone was doing reinforcement learning and trying to scale it with simulation and all that.
With the ARM farm.
Yeah, and the thing is, reinforcement learning with actor critic models have its own kind of scaling dynamics, and they are mutually adversarial. So it's really hard to get the data, and sim to real gap is very real. And RT1 kind of pushed Google to just to imitation learning and into that scaling era. So here we found that if you have data for a task, you can just learn it. And then you can collect data at scale. You can collect data in rather with a lot of variations, and then the models tend to interpolate and also extrapolate around it.
What about the VLM base, right? That doesn't have the imitation learning baked into it, right? It's pretty close to a standard multimodal LLM, right? Like it's actually pretty much vanilla Gemini underneath. Is that right?
Yeah. So I think the idea is that, yeah, if you use these large models, they are much better compressors of this data. And they can kind of stitch concepts from the internet onto robot data. Previously, these two fields were like so separate, and now they're like coming closer together. But if you think about it, it's crazy that they are separate, right? Like everything that I do in the world, like for me to make coffee, I need to first like see and perceive, and it is all the things that an AI, like a multimodal AI, can do. So there's no reason. It's even crazy to think that they were two separate fields.
Now I'm very interested in a property of the VLAs, and we'll talk about this later, but one of the things that the multimodal LLMs still aren't very good at is understanding spatial relationships during image generation. And I wonder if embodiment just straight up fixes that. It'll be very interesting to see.
What kind of spatial relations?
Like it's very difficult to get the model to actually put objects in space in the image it generates in the way that you want. So like put the green teapot on the red book, etc. It's still not very good at that in general. Like it doesn't generalize spatial relationships very well. But maybe there's a way to do that now that we're giving them bodies. That could be very interesting. Do we have something resembling scaling laws for robotics today?
Yeah, I think the scaling laws in robotics are very empirical, and this is because, like it's not as strict as the Kaplan et al. Type line of work. Mainly because a lot of you need very good evaluations
Yes.
to determine the scaling laws. But if the evaluations are on robot and actually in the real world with robots, which are like slight variations can lead to very different results. Like the cup rolling away
Yes.
versus actually picking up the cup is like a small difference, right? So
So you're saying evaluation is hard,
yeah,
relatively
and
speaking.
that is why there is no the scaling laws are very empirically understood. People have built very strict and clean scaling laws in simulation, where now you can control everything, you can vary, ablate things. However, and this is work from TRI. However, we see that these simulation scaling laws don't necessarily transfer to the real world. There is
So-
some
So it might be even more jaggy than sort of LLM capabilities. We saw a great talk from Helen Toner about sort of jaggedness at the frontier, and maybe we should expect jaggedness at the robotics frontier as well because of this property. But it's just not smooth.
what's jaggedness.
So the jaggedness is the idea that basically even if general capabilities seem to advance, it's going to be really good at some tasks and really bad at others, even though these tasks seem to be of similar difficulty or even the same class. Is that something that you see, to sort of following up on Gary's question there? Like when you see failures, do you tend to see the failures for a particular task? Like, okay, it's like really good at picking up this pencil, but if you like slightly rotate it, it can't do it anymore. That's an example of jaggedness.
I
I will let you ask a question, I promise.
that doesn't quite square um with my observations playing with these models. I have generally noticed that like it's like a rising tide lifts all boats.
Right.
So the better models are generally much better at everything.
Got
And
it.
usually when you have jaggedness is often because you didn't collect the right data, and your data set has a bunch of gaps.
Got it.
Or sometimes it's also a limitation of robots, like especially humanoids haven't had that much evolution. So sometimes, like for example, they can do something like they can't like fully turn their wrist, so they cannot pick up an object. So picking up a very long object horizontally is like this, but then now picking it up in a kept like this is like this.
Okay.
You can't just do it.
Okay, I'm going to ask you one final semi-technical question. I'm going to hit you with some rapid-fire, overrated, underrated questions, and then we're going to open it up to the audience. Sounds good? Okay, so my last technical question is, yes, reinforcement learning was the dominant paradigm, reinforcement learning work on robotics has continued. And we've seen, for example, the sort of really recent multi-body work where they, took a quadruped and like cut off its leg and it could still walk around. We're seeing RL succeed in this sort of chain of thought style post-training in LLMs. What, if anything, is the future of RL in robotics currently?
So the quadruped work where they cut off its legs, which was very brutal to watch. Um,
You
and
you
not
have to
necessarily.
watch the brutal robot videos because once we have to fight them, you need to be prepared to do this.
I disagree. I've spent so much time with robots that if someone harms a robot, I would feel so bad.
That this is how this ends. No, but please talk about the reinforcement learning. Please, it's a future of reinforcement learning in robotics.
Yeah. So for locomotion, RL is king. You can learn a lot of these things in simulation, and it transfers really very well to the real world because the contact dynamics are kind of very similar, and it's low contact. However, for manipulation, RL is still kind of the way I think the correct way to make RL work is to make them work on top of the VLAs and not in a separate
Right.
in a completely separate island. I think
So you think
that
there's a
would not be
direction
very
there?
general.
There is a direction there for
Yeah,
sort of RL rollouts on top of the VLAs. Yeah, but
definitely.
fascinated to talk to you about this after. So I'm going to give you probably about 4 or 5 questions. Your only answer is allowed to be underrated or overrated. Deal?
Okay.
Okay. Um, video models for robotics.
Underrated.
Humanoids.
Underrated.
Sim to real.
Overrated.
Task verifiability.
Underrated.
That's all I had. So I'm going to open it up to the audience now. Gary, you had your hand up like 5 times, so you got it first.
You know the Wozniak coffee test, right? You
Correct.
go into an arbitrary kitchen. I'm trying to figure out how close we are to that. So there are a number of things that I notice here. So one is I don't really know what your measure of progress is. Is that accuracy? And then a second thing relates to the jaggedness, which I think is driven by distribution shift error. So you get jaggedness, which is to say you get failure on systems where they're doing relatively well in general. I think when you're forcing the system out of the distribution. So something like the Wozniak test, when I send you to a novel home, you're out of the distribution. And that's kind of the money test of generalization. And then a lot of your tasks, it seems like you're doing like 3 out of 4, which kind of reminds me of LLMs. But that means you're still making a lot of errors. And if you're talking about like a humanoid robot in a home, 1 error in 4 could actually be pretty dangerous. So like, when is it that we could actually like safely turn a robot in a home, go make a cup of coffee, you haven't been there before, do the exploration, make the cup of coffee? Like, how far away is that?
I think making a coffee, so it depends on how the coffee needs to be made. So if you think about it, uh, dexterity, that's very general, is still far away. Uh, but you can design that task in a way that doesn't require a lot of dexterity, and then you can solve it in a lot of different homes. I think doing it safely with 100% accuracy is probably still farther away. But doing it relatively, uh, uh, all of these are relative terms, right? Like I think only if we make a benchmark will we know exactly how well we can do it.
Could I read that answer back to you and see if you agree? So you're saying that the variability in the environment is not as important as the dexterity required to perform the task in the first place.
Yeah, because if these VLMs, they are trained on the internet and all of this video data. So for them, X home versus Y home is not very different. The only difference is the semantics of the task. Let's say in a certain home where you have to like search for all the ingredients versus in another home where like everything is laid out and you just have to do the task. So those would be the different difficulties that I would think about.
All right. Nathan.
We just took a robo-taxi ride from Tesla.
Hell yeah.
Just got me thinking
Was
about
there a guy in it?
There was.
Yeah.
He was instructed not to talk to us, and we made him laugh a couple times, but he otherwise held to that. So that just got me thinking about like modalities of input? Like, is this all cameras? Is there a sort of proprioception thing that's kind of being fed back into the model, or are we all in just like it's seeing its hands and it's just purely from the visual that it's able to do what it's doing?
Yeah. So I think vision is not enough to solve all of these. Yeah.
But is it currently working from just vision, or does it have other sensors already?
Not a lot of other senses, but I think that's just because like we don't have very good tactile sensing to solve uh very good tactile sensing that also doesn't take away from dexterity. Like we don't have very good hands on the market that have very good force and tactile sensing yet. It's like an engineering bottleneck.
Is that what limits when I watch the robots grab like a bag of chips? It gives me a little ick where I'm like, it's like kind of manhandling the. Yeah, they pack enough air in there. The chips will probably be fine, but it still just looks like unesthetic to me somehow. Where it grabs the chips, and I guess I'm wondering like, are we close? When do you think you'll start to do the sort of really kind of fine grained sanding down? Like we do have the language models now that are like in a way quite tasteful, where these things are kind of you're kind of oh, it
When
kind
will
of drop that orange from like 8 inches.
When will robots stop being aesthetically displeasing?
I know you love them now.
Um, I think different platforms are evolving at different rates. So, like the Alohas are running ahead a little bit than the humanoids, and the humanoids are running a little bit behind. Um, but that problem of aesthetically picking up chips is a lack of force and tactile sensing because you don't know how hard you're pressing that. I think China is very good at iterating on hands and stuff. I think like the hardware is evolving very fast. So I do expect that a lot of these hands will be on the market soon, and a lot of these capabilities will be accessible to researchers soon.
Who in the room is in policy and from Washington? Hands up. We need to kick off the robotic supply chain like yesterday. I'm getting really tired of saying this. Make it happen. Sorry, you had a question earlier.
Yeah, I was just curious about the training. So in one of the videos, there was like a guy operating hands, and the robot was being trained to imitate him. And then you said it transferred also to like a differently shaped robot. So I'm curious, like, I guess like how much human demonstration data goes into this, and then also like why is it that you can map from like a different set of joints, one set of joints to a different set of joints? Does it map to the humanoid without anyone even operating the humanoid ever?
Yeah, so that is, or I think you still need a little bit of humanoid data, but you get a lot more capabilities that you didn't explicitly collect for. And this, my hypothesis is that this happens because you're learning on a more semantic level.
So, and just on like a super basic level, with the humanoids, you're also operating the humanoids, right? So, so they operate the like. Is someone wearing a suit, or like how does a human operate the humanoid to like generate the data?
Yeah, so different companies have different approaches to how to collect the humanoid data. Some people have motion capture suits, some people have VR teleop, some people have just line of sight teleop. Teleoperation itself is a whole research field, and all of these could get you data, but and different qualities of data. For example, VR has maybe a little bit of lag, motion capture, or some people even have the Apple Vision Pro, but there now you have bad data around occlusions and stuff. There are many different ways of collecting this data.
Thank you very much for sharing your research. So I work in the labor market, and I'm thinking about work. Um, and one of the things that's the most important driver of the pace at which generative AI has affected work is firm adoption and the economics around it. So I don't have an intuition for the economics here. I understand there's a fixed cost of robots. I understand there is a cost of operating, which I presume is something like power. Um, there's maintenance and so on. For the layer of sort of, I don't know what you call this, the thinking and the sort of control, this is not my area of expertise, right? So like, the stuff that you're working on here, should I assume that long term, the cost of that sort of approach is zero? Like, do you think of that as being like quite, how much does it cost? Or do you think it like will sort of cost to operate these things in the field for the layer that you work on? If we put aside the cost of like making robots and power.
I think so. This is a longer term question, right? Like around commercialization and where the asymptote will get to. If you talk about the asymptote of where the physical AGI will go, I think at some point it will just be like Gemini. Gemini will be able to control robots out of the box without any specific new model or strategies. So then I think the cost will start looking a lot like how much it costs to run Gemini.
I came in late, so I apologize if someone has already talked about the Rodney Brooks dexterity paper. Did that come up?
We have not talked about the Rodney
Okay.
Brooks dexterity paper.
Okay, so Rod Brooks published this paper a week or two ago called, I think, just dexterity, and he argues that basically the main obstacle to cracking the problem of dexterity is that the number of sensors that our human bodies have in order to be able to manipulate objects is just insanely large, and it's nerves and surface of our skin, it's various skeletal muscles, it's all sorts of things that let us feel the weight of an object, how to manipulate it, how fragile it is, and so forth. And so there is an argument that getting to like general purpose humanoid robots that could kind of do any task is not going to happen, simply because even as that improves, it will just be really crazy expensive. It's never going to be economically viable to build a machine with that many sensors, that much hardware, that it can allow it to emulate human tasks sufficiently well. So I guess that's my question. Do you think we will get to that level, or is it more like we'll have a coffee making robot, we'll have a laundry robot, but we won't have a robot that does it all?
Um, I'm very much on the side that we'll have very general purpose humanoids that can do all sorts of things. And I don't think that you need like to model the skeletons and stuff. I think if you have a very good hand brain, you need to model the hand really well and the brain really well, and everything else is a mapping problem. Um,
Have you read
yeah.
that paper?
Huh?
Have you read it?
I think it came from the 2 weeks ago or something, right? I haven't fully read it, but I think I understand the general idea.
So you're not quite addressing. I haven't read it yet either, so I also have it secondhand. But I think a bunch of the argument is about sensors. It's not just about the effectors in the hand. It's about being able to build a complex model of what the object is that you're lifting, its physical properties, etc.
Yeah, so to simplify that a little bit, so you need very good touch sensing and you need force feedback, right? Because that would cover how fragile the object is and how it feels or how soft it is. That's all and then vision. So that's all you need, right?
I have a question about the motion transfer and task transfer. You showed amazing examples there. If the humanoid robot data has already been in the training set, why do you call it as a motion transfer? Is it because the humanoid data hasn't been teleoperated to do the exact task?
Or those motions.
Yeah.
Yeah.
Of the exact those motion. Okay. Then it's okay. It's more like a task transfer then. So maybe the question, final question. So it seems like the dexterity you showed in these examples is enough for the robot to see a schematic of a IKEA furniture assembly. And then how far for these robots can really just read the picture and then assemble a very simple IKEA furniture?
Yeah, I think very close. Maybe there was some paper which had even a benchmark that was literally IKEA assembly, and
A special issue of AAA magazine that I edited.
yeah, and I think very close, yeah. But maybe like everything is like long tail, right? Like the hard IKEA assembly would take a long time, but a lot of the easier ones soon. I think yeah, this is from Generalist AI. The IKEA assembly.
I think the first version of that, which we were not allowed to call the IKEA test, was in 2016 in a special issue that Manuela Veloso, Francesca Rossi, and I edited of AAA magazine. We called it the Turing Olympics. The issue as a whole, and there were about 14 tests, and one of them was that.
There was an update from Generalist AI just this month.
Okay.
But it is about IKEA assembly.
All right, they stole it from us.
All right. That's it. Thanks everybody for attending. I hope that you've been as wowed as I have been. I have many questions. It's just fantastic. Thank you so much, Keerthana.
Thanks for having me.